So we started last time, this is where we left off, was talking about topologies. And we went through this really fast, but I wanted to go a little bit more detail here. So far, in this class, we've been talking about buses. And actually, buses are a type of interconnection network. So a multi-drop bus, where everyone just sort of screams, is a broadcast network. And it is a type of interconnection network. But it may not have the best properties. It may not have the best bandwidth. And it might impact your clock frequency, so it might even impact your latency, depending on how you go about implementing one of these things. So sort of the next step away from something like a bus is actually something like a pipeline bus, where you start to put registers in along the way. And now you can have nearest neighbor communication. Let's say 1 is talking to 2 and 3 is talking to 4 at the same time. But you couldn't do that when everyone was shouting to each other. Because only one entity is allowed to talk on this bus at a time, we'll say. So we start thinking about that. And we can actually make some more advanced versions of these. We can start to think about things like toruses, where we'll take the end here and connect it around. And this is a one-dimensional torus, or many times is known as a ring. One thing I wanted to point out about this is if you look at the naive ring implementation, and if you think of these as wires, you would say, well, this is interesting. If I have 1,000 nodes in my ring, let's think about that. 1, 2, 3, 4. Yep. OK, if you have 1,000 nodes in my ring, 999 of them are going to have very short links. And then one of the links is going to be super, super long. It's going to go from this end all the way to that end, like this is drawn. Well, that's not super great. Conveniently, people have actually thought of fancy ways to fold toruses into let's say if this is a 1D torus into a 1D space, and minimize the wire lengths. So actually, I drew a picture here to show this. If you renumber and stagger the way you connect the nodes here, this is the exact same 1D torus as we drew here, except now all the links are equal distance or equal length, except they're twice the length as they were before. So you can actually fold a torus into the same, for instance, an n-dimensional torus into an n-dimensional space by doubling each of the links by doing this cool interleaving trick. And this also applies for 2D, 3D, 4D toruses, et cetera. You can come up with some ordering and numbering which will actually interleave like that. Now, having said that, it may be challenging to build a 4-dimensional torus in 3 space. And unfortunately, I live in 3-dimensional space, and I'm hoping you guys do too. And if you're like me and you live in 3-dimensional space, it can be hard to go build 5-dimensional things in 3-dimensional space. We'll talk about that in a minute. But I just want to show this cool trick that you can actually fold a 1-dimensional torus into a 1-dimensional space and not have a super long link. OK, so now we can start to think about, actually, before we go on to that, let's think about the limits of this. If we start to go to 1,000 long torus, or 1,000 1D ring or 1D torus, unfortunately, this does not, the amount of sort of bandwidth that you cut through, let's say, these 2 links here, does not go up as we add nodes. And a good property of a network, or an interconnection network, is that as you add more people communicating on the network, or more entities communicating on the network, you probably want to be able to add more bandwidth. And you could say, well, I can make the links wider, but that only helps so much. Or I can make the links faster, but that only helps so much. So this makes us think about having different topologies. So we can start to go to higher dimensioned topologies. So we can start to use 2D topologies, or 3D. And you can see here, we have, let's say, 16 nodes arranged in a 2-dimensional mesh, versus here we have a 2D torus. And the difference between the 2D mesh and the 2D torus is that there's what's called end around in the torus. And that makes the routing from here to there much, much faster. And effectively will cut the average routing time, or average hop count by a half, because you can go either way now and go around the ends. Sometimes these 2D toruses are called a 2D mesh with end around. That means it's a torus. I just want to throw that nomenclature out there, because sometimes you'll see both. A good example of a simple routing protocol is if you're at this node here and you want to communicate some data, you can send the data in all directions, and then everyone else sends it in all directions, everyone else sends it in all directions, and it'll just flood the network and it'll get everywhere. And you guarantee that it's going to at least get to the receiver, and you have some guarantee that when it gets to the receiver sees the packet and takes it off. Now that may not be what you want to do. That's probably not low power, and it's probably going to cause a lot of congestion on your network, but you could think about a flooding protocol. OK, so wherever there is 2D, we can start to go to 3D. So here we have a 3-dimensional cube. Sort of, it's best I could draw. It's hard to draw 3-dimensional things on a 2-dimensional space. And if we had 3D space, I could have drawn this much cooler. So this is a hypercube. Both these are actually hypercubes. So all a hypercube is it's saying that the number of dimensions you have is equal to the number or the degree or the outbound links of a node in here. So if you look at this node, we have a 3-dimensional hypercube. So it can go this direction, or that direction. Every node has an out degree of 3, or a connectivity of 3. Here, we have a 4-dimensional cube, but this is by definition a hypercube. So because if you look at any given point here, so we're going to define a hypercube as the out degree of the nodes is equal to the dimension of the links. And you can't go build here if you were to add one more node to this system, or some other, let's say you were to scale this out in some direction, you would actually be increasing the degree of a node by adding more nodes, but not to everybody equally. So it would not be a hypercube. So if you were to build, I don't know, something like this network here, this is not strictly a hypercube, because the degree of, let's say, this node here is not equal to the degree of, well, actually, let's think about that. The degree is equal to the degree of the other places, but we've effectively increased the diameter of one of the dimensions such that there's not, the routing distance is longer now for this number of nodes. If you were to go to a higher dimensional design, you could actually reduce the latency for each one of these nodes in something like a 3-dimensional 3 cube, which we'll talk about in a minute. But here, we have a 4-dimensional cube. And what's nice about this is the number of hops to get from here to anywhere else is quite low. So let's think where the farthest point in this cube is going to be. So it's going to be, let's think, is it here or is it here? 1, 2, 3. No, it's the other one. OK, so it's going to be 1, 2, 3, 4 to get to there. It's going to be the farthest number of hops. So we can think about having these higher dimensional systems. Now, as may be readily apparent, but I'll say it anyway, if you try to build a 5-dimensional hypercube in 3-dimensional space, some of the wires are going to get long, because you can't fold 5-dimensional space into 3-dimensional space. you might be able to bend, for instance, a 4-dimensional space into a 3-dimensional space with not too bad. But there's kind of this good rule of thumb when you're building networks that you probably don't want to be building you probably want to try to map, let's say, an n-dimensional network into an n-dimensional space. Trying to map higher is painful. Trying to map much, much higher is very painful. The benefits, though, is that you have to have fewer routing hops to be able to get to wherever you're going in the higher dimension cube. Now, I wanted to throw this one up here because this is an interesting topology. Just connect everything to everything. This seems great. We should all build these networks. Unfortunately, let's think about trying to put this network in 3 space if we have 1,000 nodes. Well, what that means is if you have 1,000 nodes, each node is going to need to have 999 outbound connections and 999 inbound connections. So when you go to build this, you might be able to build it sort of outside of a sphere or sort of a big wiring mess on the inside. That's pretty hard to do for large numbers of nodes. For small numbers of nodes, something like a fully connected crossbar or what's also known as a star topology will probably work fine. But and in fact, if you cut it sort of across the middle of the network here, which we'll talk about in a second, it has very good bandwidth. OK, a few other things you guys should know about from a terminology perspective. The networks that I've drawn up to this point are what are called direct networks, which means that the nodes have some type of router built into them. You could also, and plenty of people build this, is they build networks where the nodes do not have the routers built into them, but there's a multi-stage network or some sort of network in between the nodes. So a good example of this actually is something like your internet, if you will. There you have computer nodes, and the computers are not doing the routing themselves. Instead, they send it out to what we'll call an Ethernet switch. And the Ethernet switch is, let's say, one of these boxes here in the middle. And that makes a decision and then sends it on further. Or there could be an internet router, could be in the middle here also. And the analog in computer architecture of what we're building is you can think of building these massively parallel machines, something like a massively parallel Cray machine or something like that. They actually have multi-stage networks in the middle here, and all the nodes kind of sit on the outside. Note the way I numbered this. This is the same thing as that, but I just didn't want to draw the wires going around. So here we're sort of drawing as if data is flowing strictly from left to right. And what we did here is we have 8 nodes. And what you'll see here is there's log 2 number of stages here if you have 2-to-1 switches along the route here. And something like an omega network actually has only one path between each point. So if you want to get from here, let's say 8 to 3, you're going to have to go here, here, there, there. You can't, there's no other paths you can take. So let's say you routed straight at this first decision point and went here, and you went up, you're never going to be able to get up to 3. This is in contrast to some other multi-stage networks where people actually put in extra stages in the middle here. And this gives you some path diversity. So it'll allow you to route around maybe congestions or route around problem links. If we were to add one more stage, it looks exactly the same as the rest of these stages. Because if you look here, all these stages have the same wiring in the middle, you'll note. If we add an extra stage, we'd actually be able to have multiple links or multiple paths between the endpoints. And sometimes that's good. Another type of network here that you can build is a tree. It's an interesting topology. What you probably want to do if you're building a tree, though, is And if you want to be able to communicate, let's say, from this half to that half of your machine, you're going to want to somehow make the links wider as they go higher up in the tree. And that's what we call a fat tree. So a fat tree doubles the links each level up in the hierarchy. And then you have, let's say, this node, when you communicate with that node, there is enough bandwidth across this backplane here to support lots of nodes over here communicating with lots of nodes over there. One other interesting thing about a fat tree is if you go and try to implement this across a 2D space, we'll say, and you try to map this into a 2D space, it actually starts to look pretty similar to a mesh at some level, except it looks like a mesh that you've removed links from. So think about that if you ever go to sit down and build a tree or a fat tree. It actually looks just like a mesh, except when you go to do the mapping of this, you'll basically see that there's this node and this node are very close in the two-dimensional layout. So you could just run a local wire, a sneak path between these two. And then you also realize that this one and this one will be really close. So you just run a sneak path between them. So to some extent, some of these topologies may not make as much sense in a certain packaging or a certain layout in physical space. But if you, let's say, have multiple chips, something like a fat tree may make sense. So I want to introduce a piece of nomenclature here that you'll see for mesh networks. That you'll hear sometimes people talk about things as k-ary n cubes. And this is using two numbers, we can completely describe a type of mesh network. And we're going to use two numbers here. The first one is k. So if you say 5-ary, what that means is this is the number of nodes in any one dimension. And the n here in our n cube is the number of dimensions. So this gives us a way to describe things that are not strictly hypercubes. So we can describe sort of other shapes, but that are still some sort of cube. So for an example here, we'll look at a 3 by 3 by 3 cube. So this is kind of like a Rubik's Cube or something like that. And each one of the blocks in the Rubik's Cube corresponds to a node that wants to communicate. And this is actually a 3-ary, 3-cube mesh with no end around. And we can see that the worst case path length in here is going to be from here to here. So it's going to be 1, 2, 3, 4, 5, 6. Is that right? 2, 3, 4, 5, 6. That's how many links we need to traverse to get from here to the farthest away other point in the system.